Hello. Last time we talked about MC delta T and how we can calculate the heat, the quantity of heat that's released or absorbed by my system. So MC delta T works great, but sometimes when we do a chemical reaction, it's not as straightforward. We can't do Q equals MC delta T. For example, let's say I have magnesium and I want to react it with HCl. For this reaction, do I use C for magnesium? Do I use it for HCl? Do I use it for the products? Do I add all of them together? Do I multiply them? What do I do? So it's not as straightforward. And so we use the first law of thermodynamics, which basically said that the energy of the universe is conserved, is fixed. And so we know that the universe is made up of the system and the surroundings. So together they make up the universe. We know that the quantity of energy in the universe is conserved, but we know that the system can release energy to the surroundings, or the surroundings can give energy to my system. So the idea is that one gives off the energy, the other one absorbs that energy, and it's the same amount of energy that's released or absorbed. So we can measure the amount of heat indirectly, and that method is called calorimetry. We use a calorimeter to measure it, and it's called calorimetry because you're measuring the calories or the amount of heat. So we know that when heat is released, your delta H or your Q is negative. When heat is absorbed, your delta H or your Q is positive. Remember, delta H and Q are the same thing, right? They're both are the heat that is transferred. So what we can say is the Q of system is equal to negative Q of surroundings. What does that mean? So if my system, let's say my reaction is exothermic and it's releasing 10 kilojoules of energy. Well then, when it releases those 10 kilojoules, what takes in those 10 kilojoules? Well, the surroundings takes them in. So the surroundings, our Q is positive 10 kilojoules. So the system releases 10 kilojoules, the surroundings absorb those 10 kilojoules. That's if your system is exo. What if your system is endo? So let's say my system absorbs, so positive 5 kilojoules. Well, where is it getting those 5 kilojoules from? They're getting it from the surroundings. Q of the surroundings are going to be negative 5 kilojoules. So the system absorbed 5 kilojoules from the surroundings. So when we say Q of the system is equal to negative Q of the surroundings, we're not saying the surroundings are negative and the system is positive. We're just saying they're opposite signs of each other. So when one is positive, the other one is negative. Well, if we know that, what we could do is we can say, well, Q of my system is equal to negative Q of my surroundings, and Q of my surroundings is MC delta T for the surroundings. M of the surroundings, C of the surroundings, and delta T of the surroundings. And if we can measure the mass, the C, and the delta T for my surroundings, then we can figure out what Q of the system is. You could also say, well, Q of system is MC delta T of the system. Q of surroundings is MC delta T of surroundings. So if Q of system is equal to negative Q of surroundings, then MC delta T of the system is equal to negative MC delta T of the surroundings. We would use this if we're trying to solve for the mass of the system or the C of the system as one of the delta T or one of the temperatures or something like that. So how do we actually do this? So we use a calorimeter. So this is a picture of the calorimeter that we're using in class. It's basically 2 styrofoam cups inside of each other for just insulation. And then half of a styrofoam cup that has a hole in it, and a thermometer. This is our, what we call coffee cup calorimeter. So this is a picture of a coffee cup calorimeter. So how does that work? Well, let's say I have my magnesium and my HCl. So my HCl is dissolved in water, right? It's a solution. It's mostly water with a little bit of HCl bubbled in it, right? So what I do is I put my HCl in here, which is a solution, it's mostly water. I mass that water, that solution, write it down. I measure the initial temperature of my solution, my HCl solution, write that down. And then what I do is I drop in the piece of magnesium, cover it, and use my thermometer to stir and watch the temperature. Because my reaction is exothermic, it's going to produce heat. That heat is going to go into the water that's in my solution here, and it's going to make the temperature rise. So then I record my final temperature. So right here, if I want to calculate delta H of my system or Q of my system, I would say, well, it's equal to negative Q of my surroundings, which is MC delta T for the surroundings. The surroundings are the water or the solution, right? So I can easily mass the solution. I can look up the C for the solution. It's basically C for water because the solution is mostly water. And I can measure the initial final temperature of my water, my solution. And so I can calculate delta H for my reaction of magnesium and HCl. Let's say I want to know how many calories are in an apple. How do they do that? So they do a similar thing, except their reaction is not in water. They have something like this, but obviously a lot more insulated in food labs, where it's called a bomb calorimeter, actually, where you would take your apple, you would dehydrate it, remove all the water out of it, and then you put it in here. There's a chamber that has oxygen in it, and it has a spark. So you light your apple, right? It ignites. As it ignites, it gives off heat. And that chamber that has your apple in it that's burning is surrounded by water, and that is all insulated. And they mass the water before they start. They measure the initial temperature of the water before they start. When the apple burns, it gives off heat to that water. It rises its temperature, so they measure the final temperature of the water. And then again, they say, well, the heat that is released by the apple is equal to the heat that's absorbed by the water. And so Q for the apple would be the mass of the water times C for water times delta T for water, and put a negative sign in front of it because it's the opposite. And that's how they calculate the calories that are in food. So the idea of calorimetry is to indirectly measure the heat that is transferred. So as soon as you realize that it's a calorimetry problem, the first thing you want to do is write Q of system equals negative Q of surroundings. Then you want to ID your system and surroundings. What does that mean? Like, identify what they are. So is your system dissolving? Is it delta H of dissolving? Is your system a chemical reaction? You just write delta H of reaction. Is your system a piece of copper that's being heated? So it's Q of copper. What is your system? And same thing with surroundings. What are your surroundings? Are they water? Most of the time they are. Is it a solution? Is it something else? So write Q of system equals negative Q of surroundings, then ID your system and surroundings, and then decide, do you break it up as equation A or equation B? So do you make both signs, break sides both into MC delta T's, or just one of the sides? You use A when you're solving for Q of system. You use B if you're solving for the mass, the C, or the temperature. So let's look at a couple of examples. Number one says, when a 4.25 gram sample of solid NH4NO3 dissolves in 60 grams of water in a calorimeter, the temperature drops from 21 Celsius to 16.9 Celsius. We want to calculate delta H for the dissolving process. So I know automatically this is a calorimetry problem because it says calorimeter right there. So as soon as I see that, I write Q of system equals negative Q of surroundings. Then I ID my system and my surroundings. So what is my system? What is happening? Well, looks like I'm taking ammonium nitrate and dissolving it. So you can call your system Q of NH4NO3. You could call it delta H of NH4NO3. You could call it Q of dissolving. You could call it delta H of dissolving. You could call it delta H of solution because you're making a solution. You could call it anything that you want that makes sense to you. I'm going to choose to call my system delta H of dissolving. Why did I pick this? Because in the question they're asking me for delta H of dissolving, so that way I don't get confused. So that's my system. What are my surroundings? Well, it looks like I'm taking that NH4NO3 and dissolving it in water, and so water is my surroundings. Okay? Next, choose. Do you break up both sides or only one side into MC delta T? Well, what are you solving for? You're solving for delta H of dissolving. So you want to keep this to say delta H of dissolving, right? I don't want to break that up because that's what I'm solving for. So I'm only going to break up one side. So I'm going to say Q of water is MC delta T of water. And now, at this point, you just plug in your numbers. So delta H for dissolving is going to be equal to negative M for water, because this says water, right? So M for water, mass of water is 60.0 grams. So why do they give you that 4.25? Just to distract you. You don't need it. C for water is 4.186 joules per gram Celsius. Delta T for water is final, so 16.9 Celsius minus initial, which is 21 Celsius. That's going to give you Q of the dissolving. Looks like my temperature went down, so that means my system is endothermic. So delta H for dissolving should be a positive value. Let's check. It turns out to be a positive value. It is positive 1,030 joules. My grams cancel, my Celsius cancel, and I end up with joules. So that's my answer. Let's look at another example. We have 30 grams of copper at 320 Celsius, very, very hot, mixed with 120 grams of water at 40 Celsius, a little bit warm. Find the final temperature of the system. Now, I'm taking a very hot copper piece and I'm putting it in water that's at a cooler temperature. So my copper is going to give heat to my water, right? So the reason why the copper will give heat to my water is because copper is at a much higher temperature than the water. So the copper is going to keep giving heat to the water until they reach a final temperature. We want to know what that temperature is. This is the calorimetry problem. How do I know that? Because I have two different substances, one giving heat to the other. So I'm going to consider one of them as a system, one of them as a surroundings. So if you have two different substances starting at two different temperatures, that's a calorimetry problem. So I'm going to start by saying Q of system equals negative Q of surroundings. Next, ID your system and surroundings. Well, I have copper and I have water. It doesn't matter which one you pick as your system, which one is your surroundings, but I'll say Q of copper equals negative Q of water. If you said Q of water equals negative Q of copper, same thing. Next, I decide, do I break up both sides into MC delta T's or just one? Well, I probably want to do both because I'm looking for the final temperature. So if you're looking for mass or C or delta T, you probably want to find, you want to break both sides up. So MC delta T for copper is equal to negative MC delta T for my water. And now it's a plug and chug problem. So mass of copper first is 30 grams. C for copper, you look that up on your table. It's 0.387 joules per gram Celsius. Delta T for copper is delta T is T final minus T initial. T final is what we're looking for, right? My initial is 320 Celsius. That is equal to negative. Mass of water is 120 grams. C for water is 4.186 joules per gram Celsius. Delta T for water. It's T final minus T initial. T final is the same as the copper T final because the copper is going to give energy to the water because the copper is hotter, right? So it's at a higher temperature. So I'm going to keep giving energy to the water until they're both at the same temperature. So your final temperature for both is going to be the same. T final for both would be the same. If it helps you mathematically to put X instead of TF to help you solve for it, you can do that as well. So from there, that's algebra to solve for TF. So basically you want to multiply those two together. That gives you 11.61. And I'm going to multiply those two together. This gives me negative 502.1. And next we're going to distribute, right? So you get 11.61 TF minus 3,715 is equal to negative 502.1 TF plus negative and negative multiplied together gives you a positive 20083. Then you're going to combine like terms, so I'm going to move this to the other side by adding it, and this to the other side by adding it. So I get 513.7 TF is equal to 23,798, and then you divide both sides by 513.7. You get T final to be 46.3 Celsius, which looks like we need only 1/6 fig, so that rounds to 50 Celsius. And that's your answer. Now, I know there's a lot of algebra here, but if you have this work, like just this equation with the numbers plugged in with units, then the final answer is only 1 point. So I care about the chemistry, not you knowing how to punch it into your calculator. I do want you to look at this and see if it makes sense. Copper started out at 320 Celsius. It went all the way down to 50 Celsius. That's a lot. It's a big difference, right? Now let's look at water. When water started at 40 Celsius, it only went to 46 or 50, let's say. Does that make sense that water is only raised its temperature by 6 Celsius when copper went down by, 170 Celsius? Yes, it does make sense. Well, first of all, there's 4 times as much water as there is copper, right? That's one factor, but the bigger factor is the specific heat capacity. Look at the specific heat capacity for copper versus water. Water is more than 10 times the specific heat capacity for copper, which means that it takes a lot of energy to change water's temperature, but it takes very little energy to change copper's temperature. So that's why copper changes drastically, but water doesn't change its temperature very much.